going to go up. I agree. So let's see what happens. Sure enough, the plunger's going to your left, right? In other words, the volume is increasing. It has to. P equals NKT. T went up. P was the same, so V had to go up as well, right? And then if I put it in the ice, it'll go the other way, shrink it back the other way. So that's all pretty straightforward. If you're happy with this equation, it's easy to figure that out, right? But I think the thing to learn from this is how would you physically achieve this? There's a lot of students who will look at this equation and say, oh yeah, I've taken my chemistry class 50 times. I know how to use it. You're given a problem. You know what N is. You know what T is, or whatever. You're told some things to figure out other things based on that. But you might not realize physically how do you achieve this. How do you build a device to make the pressure the same? Well, here's how you do this one. Here's how you make the pressure the same. You just have the syringe, and then you put this thing in ice or in boiling water, and it does what you expect. So what we just confirmed is that in fact, yes, P times V. We just confirmed that V is proportional to T, or at least monotonic with it, right? In the positive sign. Because we didn't do it that quantitatively. I wasn't that quantitative. But if we did it quantitatively, we discovered, yes, in fact, it's true. P and T are proportional. V and T are proportional when P is fixed. Okay, great. So what's happening here is we're heating this thing up. The temperature is increasing. The temperature of this spot is bigger than the temperature here. We'll figure out what that is exactly in a minute. But what about the work that was done? So what happened right there was we added heat to the system, right? The temperature went up, and the volume went up, right? The pressure stayed the same. So first of all, was heat exchanged with the system? Yeah. Which way did the heat go? Did the heat go into the system or come out of the system? For which part? When I put it inside the boiling water, heat went into the system. So if I go from left to right, then Q in is bigger than 0. We know that. We added heat to the system. We also know that the temperature change was bigger than 0. The temperature went up, right? We also know, I'll put this down. We also know that, how much work was done. So here's something I do different in the book, and it's something you're already familiar with. I use lots of subscripts. The book uses W to mean work by system, but I never try to keep it straight about work by, work in. I always write it explicitly. So I have work by and work on. I have Q in and Q out. It just writes Q. So when it writes this Q in the book, they mean Q in. But when they write W, they mean work by, which I think is really confusing because they're going in opposite directions, kind of. So what I do is I put a subscript, and I don't care which one I use. I'll label it. And then once I label it, I make sure my sign is right for the one I use. So this is the one the book uses for plain old Q, I believe. Q in. And we figure out, yeah, it's positive. What about the work? And as I said, when there's just W in the book, they mean work by. I'm going to use, I tend to think about, well, it doesn't matter. I just put a subscript and I have to think about it. So which one am I going to use? Let's do work by. Was work by positive or negative or 0? Did the system do any work? Well, when I put the gas, let's do it particularly for when I put this in the hot water. So I put it in the hot water, right? The gas expands, the plunger moves. Well, there's a non-zero force, right? Because there's pressure in there. The plunger moved that way because the gas expanded. So did the gas do work on the plunger or not? It did. Is it positive work or negative work done by the gas? Positive work. So when I went from here to here, the expanding gas pushed outward on the plunger. The plunger moved. We know what work is. What is work? It's equal to, let's see, it'd be the force of gas on plunger, or what do you call that thing? I guess it's plunger. Right? Just to be clear, work by means by the system. What is the system? In this case, the system is the gas. That's what I mean by. Gas on plunger times how far the thing moved. Delta x, right? This is the x component of it, let's say. Let's say that we know that we define that way to be the x-axis, along the direction the plunger can move. So we're okay with this. You might worry, well, wait a minute, this is only valid if the force is constant. Well, as long as we do this quasi-statically, very slowly, and I didn't quite, I plunged into very hot water, but maybe if I did this, turn the temperature up slowly, right? Then what would happen is, and if I let the plunger move freely during that whole time, as long as the pressure doesn't vary too much from this constant value of 1 atmosphere, right? Then it is a constant force, right? Because what is this force? That force, right, is just, what is it? Pressure over area, right? Pressure is force over area. Oh, did I get backward? Oh, force is, well, let's see. This is newtons per, oh, you're right. Does that look better? Looks better. Bigger area, bigger force. Yeah, of course. That's why it is that my mechanic can lift my car up with his little foot. Small area on the foot, big area on the car. Yeah, that's right. Okay, so, and yeah, that's right. So, because the pressure is the same, but the force is different in that case. So very good. Given that the pressure is the same throughout the whole process, the force is the same as well. So that means it's okay for us to use this formula, but not in all cases. It's only okay because we chose an example where pressure is constant. In other words, for horizontal straight lines in a PV diagram, how can I calculate the work? Oh, it's just the change in x times the constant force. But we don't know. Usually in a problem, you're not given the forces or the distance the plunger moved. You're told about pressures and volumes. So how do we relate these things to that? Well, we know the change in the volume is. It's just going to be equal to some area times the change in x, and we know what the change in the let's see. We know how to relate. In other words, we know how to relate force and area. Oh, I didn't have it right here. They both involve this area, so it cancels out. Anyways, the work by then, when the dust clears, is just going to be equal to the pressure if it's constant. If constant. Yeah. So we're going to write this big chart. All right. If constant times not delta x but delta v. Right. And let's make sure we've got our signs right and I think our units are correct. I think everything's okay. Let's check our sign. So the work by is positive if delta v is positive, and that's correct because pressure. Remember, this is absolute pressure. It's always a non-negative number. You can have in principle 0 pressure. In principle, it's hard to achieve. Impossible to achieve exactly, I guess. But you can have. There's always a positive number, right? So that means that if this is positive, that means the final volume is greater than the initial volume. If that's true, this is positive. Work by the gas is positive. That's correct, right? So the situation we had right there, we heated up the gas, temperature went up. As a result, the volume went up. As a result, the gas did positive work, right? But that's kind of puzzling, right? Because if the gas did positive work, I mean, did the kinetic energy of molecules inside the gas go up or down during that process? Well, we know we can relate the energy of the gas, which is just the sum of the kinetic energies of all molecules of gas, right? Well, that equals 3 halves NKT. Actually, it's 5 halves. Now we forget that. We'll pretend it's ideal gas is monatomic. 3 halves NKT. So the temperature went up when I put the gas into the boiling water, right? The little cancer gas in the boiling water. So the energy of the molecules go up or down? Up. The energy of the gas went up, and yet the gas did work on the outside world, right? So it lost energy as well through that. So it must be that there must have been some compensation, right? Some energy must have been added to the system, and it was. What was that? So zero law of thermodynamics, temperature of A equals temperature of B, temperature of B equals temperature of C. That implies temperature of A equals temperature of C, right? First law of thermodynamics says, well, it says energy is conserved. This is just conservation of energy. And what it says is that the change in the energy of a system, and they use U for the energy, which is kind of surprising because you might think, wait a minute, the energy of the gas is really a kinetic energy. And before we were using PU or U as a potential energy, and then there's K. So I apologize for all the confusion, but but the book often uses U. You can also just use E. So I might write it this way. I might write it this way. I tend to write it this way because it just makes more sense to me. But whatever symbols you want to use is fine. As long as you're clear with yourself and the grader what you mean. So the change in the energy of the system, what is that? Well, it's equal to the work done on the system, not by, but on the system. They have a positive sign here, plus the heat added to the system. So heat in, right? So I like to write it this way. I like to use an E to remind me that it's all the energies in the gas, right? Happens to be kinetic energy in this case, ideal gas. And I like to say positive work on plus Q in. This keeps my head straight because I know that if I do work on the system, its energy better go up. If I add heat to the system, its energy better go up. Right? Well, I should be careful. That contribution to its energy better go up. If we just saw an example where negative work was on the system and yet the energy went up, but that's because Q in was bigger than work on. Well, let me say it this way. Q in was bigger than the absolute value of work on. Right? Does that make sense? In other words, the gas did some work on the outside environment, so negative work was done on it, but a greater amount of heat was added to the system. The net result was that the energy of the system, reflected by the temperature of the gas, went up. Okay? So like the name of the game here, as it is earlier in the semester, is about just accounting. You're going to have exchanges of heat, you're going to have work done on the system and by the system, and you'll have to consider both the work and the heat exchange to figure out what the energy change was for the gas. And some problems you'll be told what the energy of the gas is or how much it changed, and you'll be able to figure out the work. And in a lot of these problems, it'll sort of be easy to calculate what the work change was. And then with that, if you know what the change in the energy is, and if you know how much work you did, then you can figure out what heat exchange must have occurred in order to have accomplished that. Right? Just by the first law of thermodynamics, just by this, right? So this equation, combined with those two equations for ideal gases, this is always true, by the way, those are only true for a monatomic ideal gas. But those things put together, you'll be able to triangulate and figure out the missing things you don't have, right? That's the way the game's played. So if we go back to this thing and think about what exactly is the work performed in that case. So in that case, we had a constant pressure situation that allowed us to say with constant force. We had a really simple formula. We got to write from that. The work by the system is equal to P times delta V. I said, wait a minute, we need work on to use this equation. What is work on? Well, just to be really explicit here, work on is, by definition, just negative work by, okay? And so this is always true. This is what I mean by these things. When I put a by there versus an on, I just mean change the sign of it. So in other words, work by would be positive if the system happened to have done positive work on the outside world. Right? In this case, it turns out that work by is positive, work on is negative. In this case, we just did it with hot water. We plunged it in hot water. So then if I say, all right, so now let's consider the case with constant P. For constant P, we got the formula. Now it's minus P times delta V. Why minus? Because we're calculating work on, not work by. Okay? And now we can ask, all right, what is it in this case? Well, there we have it. It's V2 minus V1. That's all that is, times P. Well, so that's it. What does that correspond to graphically in that plot? So I've got this horizontal line going from that point P. Let's call it P1. Doesn't really matter. But here, we'll call this P. No. So I guess we could call this P1 and that P2. P2 equals P1, the same. So in terms of that plot, then, what does it mean graphically to calculate the work? So I got my P1, I got my V1, V2. So come on, tell me what it is. So I'll give you a dumb answer. Is it the area beside the curve? What is it? Area under the curve. So that's it right here. And we know that it's positive for all the arguments we've already made. By it, I mean work on. Work on is negative in this case, right? Work by was positive. We know that based on the arguments we've already made in these formulas, but in terms of the magnitude of that quantity, if you just want to know what is the size of this, it's just given by this area, okay? And that's always true. Even if you don't have a horizontal straight line, it's easy to do the integral. I mean, what integral, right? We just wrote down delta V times P. In general, if you've got some crazy path, right, going through, from process 1 to process 2, right, well, the area under the graph, if you can calculate it some way, area under curve is equal to the work. And I'll put absolute value sign around it. It doesn't tell you what sign it is. To figure out the sign, you have to know which way you went. And so the rule is, if you go to the right, so in this case, we went to the right. We went from a small volume to a big volume. That corresponds to positive work because when the gas expands, it pushes the plunger. So the gas is always, gas is always pushed. Ropes always pull, gas is always pushed, right? Fluids always push. So the gas is pushing out in absolute pressure. So the gas is pushing out, the plunger moves. Whenever you have an increase in volume, you're guaranteed that corresponds to positive work done by the gas, i.e. negative work done on the gas. So all you have to know is which way you went. In other words, no matter what crazy shaped curve this is, if you know it went from the left to the right, then you know that it was positive work done by the gas or negative work done on the gas, right? Super. It also, this can be very helpful for us later because we're going to get into engines. Right? I'm not sure I think we'll get into that a little bit next lecture, certainly by next week. And that means that we'll have to worry about curves that are closed curves that come back on themselves. And then we're going to say, oh yeah, there's area under the curve right here, but suppose you went in a square shape and around like that. Well, you get some positive work here, you get negative work down here. Real quick, let's calculate the work done in this case. Suppose we have a situation where we want P versus V. It's always P versus V. Most common philosophy used in this class, as part of the class. Suppose we do a situation like this. We start with some positive P, we'll call P1, and then we go down, well, that was positive, some big P1 I might say, and go down, we have it. Let's say we have the pressure. And we do this for a constant V, so V doesn't change. In this case, how much work is done? Yeah, 0. Without doing any calculation, we know that because the volume didn't change. Now the pressure did change, so this exact formula is not true. P times delta V is not the right formula because that only works for constant P. But the expression that says that work on equals negative integral of P dV, right, from V1 to V2. So this expression is always true for an ideal gas, right? When I say always, I mean for any system, it's not true for ideal gases, but it's always true for any possible curve you take, even if it's not constant P. So this is some function of V maybe. But in this case, you can see that the area under the curve is 0, right? All this, yeah, that's exactly what I would use to calculate for this crazy example with this funny shaped curve over here, this area of the curve. But in this case, area under the curve equals 0. So we can right away say that the work on the system equals 0. Right away, right? Easy. Now, if we wanted to add, what does this physically correspond to? How do I achieve this in the lab? I want to change the pressure, but I want the volume to be fixed. Yeah, all right, so I could do it again by changing temperature like I did last time. But this time, instead of letting the plunger move, I'm not going to let the plunger move. So here's what I'm going to do this time is I'm going to have a fixed volume. So right here I've got this volume that's made of like a metal ball, hollow metal ball. The ball's not going to change its shape. It's not a syringe. It's got a tube made of really stiff plastic that's not going to collapse or expand. And I've got it hooked up to a pressure gauge over here. Oh wow, it's quick. So there's a pressure gauge. And what I'm going to do is I'm going to take this thing and plunge it into hot water. Now, if I plunge this into hot water, heat is added to the system. But we know how much work can possibly be done in this system by the gas or on the gas. 0. So that means that if I heat it up, it has to result in what? An increase or decrease in the pressure? Increase. Got to be. Right? So let's check it out. Put it in here. See what the pressure gauge does. Is it moving? Oh, it's inching up. Come on. That's a little bit action. All right, moving. A little bit. Let's plunge it into ice and see if it goes the other way. And if the laws of physics are on our side, slowly, yeah, it's going down. Tapping's totally fair. I'm not tapping the needle, right? So what I'm trying to do is overcome the friction on the needle, right? The needle, there's a force on it, there's a torque on it trying to turn it, but there's friction. Do I do that? Otherwise the sign wouldn't go the other way, so it's got to go back up again. Sure enough, right? Very good. So I know that's a shocker to all of you, but that's anyway. So that's physically how you achieve that physical situation. I kept the volume fixed, but I changed the pressure. How do I do it? With exchange of heat, where I'm not allowing it to do any work. So if I allow it to do enough work till you reach constant pressure, that was the first demo, you get a different curve out, right? Even though in terms of heat added, I could maybe, if I don't tell you this exactly a factor 2, if I don't tell you exactly what the changes are, I can add the same amount of heat. I could add the same amount of heat in those two different cases, but the resulting physical situation is different. Why? Because in one case I allowed the pressure to come to equilibrium with the pressure in the room. In other words, I allowed the gas to do work or have work done on it. The second case I didn't allow work to occur, right? And that was the third thing there's a third thing I was going to consider. Oh yeah, that's constant. So this is constant volume. This is a constant volume process. What is that? Isobaric, I think, if it's constant pressure. Is it isochoric if it's constant? Oh, these are awful names. So you don't have to memorize those names. They're all in the book. On any exam, it'll be clear what you're being asked. Without having to memorize all these arcane names from like a century and a half ago. So what's the other thing you might think about? Well, one of them is constant. One of them is constant temperature. So what will that look like? I'm not probably letting you think about this for next lecture, but let's do the demo right now. How can I physically achieve this? Well, if I start off, we can sort of figure this out. We can sort of figure out qualitatively what's going on. In the first problem we thought about, right, where we said constant pressure, we added heat to the gas. And did the temperature of the gas go up or down as a result of that? Yeah, I didn't actually measure that for you, but essentially we let the gas go into equilibrium, thermal equilibrium with the boiling water. So that's true. The temperature went up in that plot up there when we went straight to the right. Now how about this plot right here where we go straight down? In this case, when I went down, if I lowered the pressure, how did I achieve that? I achieved that by putting the bulb into the ice, right, where the pressure went down. But putting the boiling water, it went back up again. So we know that in this case, temperature is going down. If I go straight to the right, temperature is going up. Something between these two curves is what happens if temperature stays the same. Does everyone see that? You go straight to the right, temperature's going up, straight down, temperature's going down. Something intermediate. And the answer is going to look like this. It's going to do that for constant t. And we've already figured out the direction of bigger and smaller constant t curves, right? Up here, is this big T or small t up here? PV equals NKT. P is big, V is big. The bigger these guys get, both of them, what do you get? Bigger T or smaller T? Bigger T. This is hot up here, and it's cold down here. For fixed N. For a system, for an ideal gas, it's got a fixed number of particles, right? So if I'm going to do this, how do we achieve it? Well, let's see. I got to think that for a second. I think I have to achieve it by allowing both P and V to change. Oh, here's the way to do it. So if I go back to the Elmo, and if I can figure out how to get these swage or whatever. Oh, here we go. So I've got a syringe now over here. I'm going to hook it up to my pressure gauge. If the temperature doesn't change, and I squeeze this guy over here, the pressure is going to go up. So what I'm doing now, oh, I blew it. Something didn't work. Oh, it's kind of working. Oh, it's not airtight. Oh, I didn't have it in right. Oh, man, laws of physics, they used to work. Oh, there it goes. Look at that. So you're not surprised. But if I make the volume smaller, the pressure gets bigger. And they're linearly, they're proportional, or inversely proportional to one another. And this is all at fixed temperature. Now, I got to be careful. If I do it too fast, the temperature can change. And one of my absolute favorite demos of this class is that if I change the temperature, let me do it real quick. I'll do it again next time. I'll do it right now. I want you to think about it. I got a cylinder right here with air in it, oxygen and nitrogen. At the bottom, I've got a little piece of paper. I'm going to close this guy really fast, so fast that no heat can be exchanged to the outside world. There's no heat exchange here. Q equals 0. And if I do it fast enough, this guy will light on fire. Can you see it? I'm going to go 1, 2, 3, and come on. 1, 2, 3. Oh. So what did I do? I didn't add heat to the system. What did I do? How did I change the energy in there to raise the temperature so high that it burnt the paper? What did I do on the system? It wasn't heat. Work. I did work on the system. Students will not believe me on the exam, but it's true. You can do work on a gas. All right.